Welcome to AWS DNS services. Welcome to our comprehensive deep dive into AWS DNS services. Today, we're going to explore the complete ecosystem of DNS solutions that AWS offers. And trust me, it's much more extensive than you might initially think. We'll start with a high-level overview of the entire DNS landscape in AWS, then drill down into each service with practical examples and real-world use cases. By the end of this presentation, you'll understand not just what each service does, but when and how to use them together. This isn't just theory. We'll cover actual command line examples, configuration patterns, and the gotchas I've learned from implementing these services in production environments. The complete DNS ecosystem. Let's start by understanding the big picture. AWS doesn't just have one DNS service. They actually have four major components that work together to provide a complete DNS solution. Route 53 is your primary authoritative DNS service. Think of it as your main DNS control center. CloudMap handles service discovery for microservices. CloudFront provides edge DNS resolution for global content delivery. And AppMesh offers DNS integration for service mesh architectures. What's really powerful is how these services integrate. For example, your microservices might use CloudMap for internal discovery, while Route 53 handles external traffic routing, and CloudFront accelerates global delivery. Notice the traffic flow. External users hit Route 53 first. This can route to CloudFront for cached content, or directly to your infrastructure. Meanwhile, your internal services use CloudMap and AppMesh for service-to-service communication. Route 53 Deep Architecture. Now let's dive deep into Route 53's architecture. This is where the real magic happens for DNS routing and traffic management. The diagram shows the complete DNS resolution flow, from when a user types your domain name, through the recursive DNS lookup process, all the way to Route 53 returning the appropriate IP address based on your routing policies. What makes Route 53 powerful isn't just basic DNS, it's the sophisticated routing policies. You can distribute traffic by weight for blue-green deployments, route by latency for performance, implement failover for high availability, or route by geography for compliance. The health checks are crucial here. They're continuously monitoring your endpoints from multiple AWS regions, feeding that health data into the routing decisions. This isn't just passive DNS, it's intelligent traffic management. Let me walk you through the exact sequence for setting up Route 53. Order matters here. You cannot simply jump to advanced routing policies without laying the proper foundation. Phase 1 is all about establishing DNS authority. You create the hosted zone, then update your domain registrar with the name servers Route 53 gives you. This is where many people get stuck. DNS propagation can take up to 48 hours. Phase 2 sets up health monitoring before you create DNS records that depend on it. This is critical. Always create your health checks first, then reference them in your routing policies. Phases 3 and 4 build up your DNS records from simple to complex. Start with basic records, then add weighted routing, latency-based routing, and failover as needed. The advanced features in phases 4 and 5, like traffic flow policies and query logging, are where Route 53 really shines for enterprise use cases. Creating your first hosted zone. Let's start with the foundation, creating a hosted zone. This is your DNS control center for a domain. The hosted zone contains all the DNS records for your domain. The caller reference parameter is crucial. It prevents duplicate creation. I always use a timestamp to ensure uniqueness. The comment helps with documentation, especially in larger organizations. When you create a hosted zone, Route 53 gives you 4 name servers. You must configure these at your domain registrar. This is how the global DNS system knows that Route 53 is authoritative for your domain. Pro tip, for private hosted zones, set private zone to true and specify the VPC. This creates DNS that only works within your VPC, perfect for internal service names. Health checks are absolutely critical for production DNS. They're continuously monitoring your endpoints from multiple AWS regions, providing the health data that drives intelligent routing decisions. I always create health checks before creating the DNS records that reference them. The configuration shown here monitors an HTTP endpoint every 30 seconds, marking it unhealthy after 3 consecutive failures. The measure latency option is really valuable. It feeds latency data to CloudWatch, helping you understand performance patterns. The regions parameter controls which AWS regions perform the health checks. I recommend using at least 3 regions to avoid false positives. String matching health checks can verify that your application is returning expected content, not just responding with an HTTP 200. This catches partial outages that basic health checks might miss. Let's start with the basics. Simple DNS records. These are your standard records that map a domain name to an IP address. Every DNS setup starts here. The action parameter can be create, delete, or upsert. I usually use upsert because it creates the record if it doesn't exist or updates it if it does, which is very handy for automation. TTL is important here. 300 seconds or 5 minutes is a good default for most applications. Lower values mean faster updates but more DNS queries and cost. Higher values mean better caching but slower updates. You can have multiple resource records in the array for the same name. Route 53 will return all of them, and the client will typically use the first one. This provides basic redundancy without routing policies. Weighted routing for traffic distribution. Now we're getting into the more advanced features. Weighted routing lets you distribute traffic across multiple endpoints based on assigned weights. This is perfect for blue-green deployments or canary releases. The set identifier is required and must be unique across all weighted records for the same name. I like to include the purpose in the identifier, for example. Primary US East 1 for clarity. With weights of 80 and 20, you're sending 80% of traffic to the primary endpoint and 20% to the secondary. Route 53 automatically removes unhealthy endpoints from the rotation based on the health checks. Lower TTL values are important here. 60 seconds means clients will pick up routing changes quickly. This is crucial for deployments where you want to gradually shift traffic. Latency-based routing for performance. Latency-based routing is one of my favorite Route 53 features. It automatically routes users to the AWS region with the lowest latency, based on real network measurements that Route 53 continuously collects. The region parameter tells Route 53 where your resource is located. Route 53 maintains latency data between different user locations and AWS regions, automatically routing to the fastest option. This is incredibly powerful for global applications. A user in Singapore might get routed to AP Southeast 1, while a user in Germany gets routed to EU West 1, all automatically based on current network conditions. Remember to always include health checks. You don't want users routed to the fastest region if it's actually down. Route 53 will automatically fall back to the next fastest healthy region. Failover routing for high availability. Failover routing provides active-passive disaster recovery. All traffic normally goes to your primary endpoint, but Route 53 automatically switches to secondary if the primary fails its health checks. A health check is required for the primary record. This is how Route 53 knows when to initiate the failover. The secondary record can also have a health check, which I recommend for production systems. The 60-second TTL is crucial for failover scenarios because you want clients to pick up the failover quickly. Some organizations use even lower values, like 30 seconds, for critical applications. Pro tip: test your failover regularly. Simulate failures of your primary endpoint to ensure the secondary can handle the full load, and that the failover happens within your RTO requirements. Traffic flow for complex routing. Traffic flow is Route 53's visual policy engine for complex routing scenarios. When you need to combine multiple routing policies like geolocation with weighted routing, traffic flow is your solution. The policy shown here implements a sophisticated routing strategy. US users get distributed between 2 US regions with 80/20ths weighting. UK users go to Europe, and everyone else gets a default weighted distribution. The rules section defines the decision tree, starting with geolocation, then applying weighted routing within each region. The endpoints section defines the final destinations. What's really powerful is the visual editor in the AWS console. You can see the entire decision tree graphically, making it easy to understand and modify complex routing logic. Query logging and monitoring. Query logging is essential for troubleshooting DNS issues and understanding traffic patterns. Route 53 can log every DNS query to CloudWatch logs, giving you detailed visibility into DNS resolution. You must first create the CloudWatch log group, then enable query logging. The logs include timestamp, client IP, query name, query type, response code, and resolver location. This provides everything you need for troubleshooting. Be aware of costs. DNS logging can generate significant log volume for high-traffic domains. Set appropriate retention policies on your log groups to manage costs. The query logs are incredibly valuable for security monitoring too. You can detect DNS tunneling attempts, DGA, domain generation algorithm, malware, and other DNS-based attacks. Cloud Map Service Discovery. Now let's move to Cloud Map, AWS's service discovery solution. While Route 53 handles external DNS, Cloud Map is designed for internal service-to-service communication in microservices architectures. The diagram shows the complete service discovery flow. Applications register themselves with Cloud Map, which maintains a registry of running service instances with their IP addresses and ports. What makes Cloud Map powerful is the integration with health checks. Only healthy instances are discoverable, so your services automatically route around failures. The health checks can be HTTP, HTTPS endpoints, TCP ports, or custom health checks. Cloud Map supports both DNS-based discovery, traditional DNS queries, and API-based discovery, programmatic queries. It also integrates automatically with ECS and EKS for hands-off service registration. Creating a Cloud Map namespace. Let's walk through setting up Cloud Map. It starts with creating a namespace. Think of this as a DNS domain for your services. I usually use local for private namespaces. Private DNS namespaces only work within the specified VPC, which is perfect for internal microservices. The services get DNS names like web-service.my company, local, that resolve to the current instance's IPs. For services that need to be discoverable from the internet, use Create Public DNS Namespace instead. HTTP namespaces are for API-only discovery without DNS resolution. The namespace becomes the foundation for all your services. You'll create multiple services within each namespace, each with their own instances. Once you have a namespace, you create services within it. Each service gets its own DNS name and can contain multiple instances. The DNS config defines the type of DNS records that are created, such as records for IPv4, AAA for IPv6, and SRV records for port information. The TTL determines how long clients cache the DNS responses. HealthCheck Custom Config enables Cloud Map's health checking. The failure threshold determines how many consecutive health check failures mark an instance as unhealthy. You can also use Route 53 health checks instead of custom health checks if you need more sophisticated monitoring, such as HTTP string matching or calculated health checks. This is where the rubber meets the road. Registering actual running instances with Cloud Map. Each instance needs a unique ID and its network information. AWS Instance IPv4 and AWS Instance Port are the core attributes that determine where traffic gets routed. You can add custom attributes for additional metadata like version, environment, or capability flags. In production, you typically don't register instances manually. ECS and EKS can do this automatically, but understanding the manual process helps with troubleshooting and custom integrations. Custom attributes are really powerful for advanced routing. For example, you could register instances with a version attribute, then query for specific versions during deployment testing. CloudFront DNS integration. CloudFront adds another layer to your DNS architecture, Global Edge DNS resolution. When users query your CloudFront-enabled domain, they are automatically routed to the nearest edge location. The beauty of CloudFront's DNS integration is that it's completely transparent. Users query Route 53 for your custom domain, receive a CNAME to the CloudFront distribution, and then CloudFront's Edge DNS routes them to the optimal edge location. Edge location selection considers not just geographic distance, but actual network performance and edge location load. CloudFront continuously measures performance and adjusts routing automatically. Different content types exhibit different caching behaviors. Static assets might cache for 24 hours. While API responses might have very short TTLs or no caching at all. Setting up a CloudFront distribution requires careful configuration of origins, cache behaviors, and DNS aliases. This example shows a multi-origin setup using both S.3 and ALB origins. The aliases section is crucial. This is where you specify your custom domain names. You'll need an SSL certificate in ACM for HTTPS support. Origins define your backend servers. S.3. Origins use Origin Access Identity for security, while custom origins like ALBs use HTTPS only for encryption in transit. Cache policies control how long content is cached at edge locations. Use managed policies for common patterns, or create custom policies for specific requirements. Route 53 CloudFront integration. The final step is connecting Route 53 to your CloudFront distribution using an alias record. This is much better than a CNAME record because alias records are free and can be used at the root domain. The hosted zone ID for CloudFront is always Z2FDTNDATAQYW2. This is CloudFront's global hosted zone. ID evaluate target health is typically false for CloudFront because CloudFront handles its own failover. Alias records automatically resolve to the IP addresses of the CloudFront edge locations, so there's no additional DNS lookup cost or latency. This makes CloudFront integration very efficient. Remember to configure your SSL certificate in CloudFront and set up appropriate cache behaviors before creating the Route 53 alias record. AppMesh DNS architecture. AppMesh adds service mesh capabilities to your DNS strategy. It provides sophisticated service-to-service communication with features like circuit breaking, retries, and automatic MTLS. The key insight here is that AppMesh integrates with CloudMap for service discovery, but adds an Envoy proxy sidecar that handles all the network communication. Your application code doesn't change, it just makes normal HTTP calls. Virtual nodes represent your actual compute resources, while virtual services provide stable DNS names. The Envoy proxies automatically handle load balancing, health checking, and traffic management based on AppMesh policies. All communication flows through the Envoy sidecars, which enables features like automatic retry, circuit breaking, and detailed observability without any code changes. AppMesh setup process. Setting up AppMesh follows a specific sequence. You start by creating the mesh itself, which is the container for all your AppMesh resources. The egress filter controls whether services can communicate with endpoints outside the mesh. Allow_all permits external calls, while drop_all blocks them unless explicitly configured. Virtual nodes represent your actual services and include listener configuration, health checks, and service discovery integration. The backend section controls which services each node can communicate with. Virtual services provide stable DNS names that abstract the underlying virtual nodes. This enables things like traffic shifting during deployments without changing client code. Virtual nodes are where you define the characteristics of your services. This includes what ports they listen on, how health checking works, and which services they can call. The Listeners section defines the network interface, port, protocol, and health check configuration. HTTP health checks should point to your application's health endpoint. Service discovery integration with CloudMap enables automatic endpoint discovery. As ECS tasks or EKS pods start and stop, CloudMap keeps the service registry updated. The backend section implements least privilege networking. Services can only communicate with explicitly allowed backends. This provides security and helps prevent cascading failures. ECS App Mesh integration. Integrating AppMesh with ECS requires specific task definition configuration. The key is the proxy configuration section, which sets up traffic interception. The Envoy sidecar runs with UID 1337 and uses IP tables rules to intercept all network traffic. AppPort specifies which ports your application listens on. Egress ignored IPs is crucial. It excludes AWS metadata endpoints that ECS tasks need to access directly. The AppMesh_virtual_node_name environment variable links the task to its mesh configuration. The depends on configuration ensures Envoy starts and becomes healthy before your application container starts. This prevents race conditions during task startup. Let's wrap up with a complete setup flow that ties everything together. This flow is your roadmap for implementing a comprehensive DNS strategy in AWS. The key is following the dependencies. You need foundation services before advanced features. This means health checks before routing policies and infrastructure before DNS records that point to it. Each phase builds on the previous one. You start with basic DNS authority, add health monitoring, create basic records, then layer on advanced routing, service discovery, CDN, and service mesh capabilities. The verification commands at each step are crucial. Always test that one phase works before moving to the next. DNS issues can be difficult to troubleshoot, so validation at each step saves time later. Testing and verification are absolutely critical for DNS implementations. The commands shown here cover the essential verification steps for each AWS DNS service. DIG and NSLOOKUP are your primary tools for DNS testing. Test from multiple locations and DNS servers to verify propagation. Don't forget to test different record types. AAAA, CNAME, MX Health Check testing ensures your failover and routing policies work correctly. Use Get Health Check Status to see the current status from all checking regions. For Cloud Map, test both DNS and API-based discovery. For CloudFront, verify both the distribution status and the actual content delivery. For App Mesh, check the virtual node status and Envoy proxy health. Query logs are invaluable for troubleshooting. They show exactly what queries are being made and how Route 53 is responding. Key takeaways and best practices. Let me share the key insights and best practices I've learned from implementing these DNS services in production environments. First, always start simple and build complexity gradually. Begin with basic Route 53 records, then add routing policies as needed. Don't try to implement everything at once. Health checks are absolutely critical. Invest time in getting them right. Use multiple regions, appropriate thresholds, and test your health check endpoints regularly. For microservices, the combination of Cloud Map and App Mesh provides powerful service discovery and communication management. But remember, App Mesh has a learning curve. Start with simple topologies. Monitor everything: DNS query patterns, health check status, CloudFront cache hit rates, and App Mesh metrics. DNS issues often show up first in monitoring before users complain. Finally, document your DNS architecture thoroughly. DNS can become complex quickly, and good documentation is essential for troubleshooting and team knowledge transfer.